Okay, students, in this video we're going to talk about light and the different colors of light and how light is formed. We're going to talk about a lot of important stuff that you need to know. So please have your guided notes out, Chapter 3 guided notes out and ready to go. We're to where it says colors of light. So we'll get started. Okay, sunlight. The light coming from the sun contains a continuous range of wavelengths and frequencies of light waves. So there's a lot of different wavelengths and frequencies coming from sunlight. A prism, though, has anyone ever played around with a prism? If you shine a light, I've got a picture of it right here. If you shine a flashlight into one side of the prism, it separates that white light that's coming out of the flashlight into all the different colors of the rainbow. How can we remember the colors of the rainbow really easily?
ROYGbIr.
ROYGbIr, yeah. So a prism separates sunlight into the continuous spectrum of colors. Remember ROYGbIr. What does the R stand for, guys? Red, orange, yellow, green, blue, indigo, and violet. Okay? So that's how we know that white light contains all the colors of the rainbow. We can shine light through the prism and it separates them. In fact, this is what causes rainbows. Instead of a prism, though, what's causing the rainbow? The rain droplets, right? The water droplets in the air. And that separates the white light from the sun into a rainbow. And so white light is a combination of all the colors in ROYGbIr. Okay? Now the human eye can only detect a small portion of light. We just can't see all the different forms of light. We're going to talk about all the different forms of light today. We can only pick up a small portion of light. Light is also called electromagnetic radiation. That's a fancy way of saying light. Electromagnetic radiation. And all the different forms of light can be found on the electromagnetic spectrum. We're going to study the electromagnetic spectrum and understand it a little bit better in the coming slides. The part of the electromagnetic spectrum that the human eye can detect is called the visible spectrum. I'll show you a picture of that on the next slide. So that small portion that we can see is called the visible spectrum. Okay. Here is the electromagnetic spectrum. Okay, we're talking about this whole slide is all the different forms of light. So let's just introduce them. We've got radio waves, microwaves, infrared. The visible spectrum, again, is just this small sliver of the electromagnetic spectrum. We've also got ultraviolet, X-rays, and gamma rays. All of it is just light. It's light. Radio waves are light. Can we see them? No. Are there radio waves going through this room right now? Yeah. But we can't see them. The wavelength for a radio wave is too large. The wavelength is too long for our eyes to pick up. I mean, they're there, but we just can't see them. Microwaves. You know, the microwaves that cook your food in a microwave oven. Or microwaves also are used to transmit TV signals. And so they're just a little bit longer than our eyes can pick up. Infrared. Infrared light is also just a little bit too long in terms of wavelength for our eyes to pick up. Where do we use infrared light? Your TV remotes send out an infrared light wave to your TV in order to change the channel. Okay, and then we get to this section. This section of the electromagnetic spectrum is called the visible spectrum. And this is the part that the human eye can pick up. If we if we look at a 700 nanometer light wave, our eyes perceive that as red. If we see a 400 nanometer light wave, our eyes perceive it as violet. Okay, and then everything else in between. So from 700 to 400 nanometers, we can see. Okay, and then we get to the other part of the electromagnetic spectrum. Now this part, the waves are too small in terms of wavelength for our eyes to pick up. Ultraviolet, the UV rays coming from the sun. We can't see them, but they're there. We know they're there. We can get a sunburn, right? The UV rays are causing the sunburn. So we know they're there. Now, when the wavelength gets smaller, what's happening to energy here now, guys? Are these becoming more energetic or less energetic? More. So now we're talking about waves that have a higher frequency, shorter wavelength. We get up to X-rays. Yeah, the same thing that doctors use and dentists use to take pictures of our bodies when they want to diagnose something. X-rays are just light. They're very high energy light waves. They can penetrate into the soft body tissue and take a picture. Okay? Gamma rays. We talked about these last chapter. Gamma rays are coming from the nucleus of the atom. Very high energy. Look at the frequency of a gamma ray. Very high. These have so much energy they can go through your body, break DNA inside the nucleus of your cells, and sometimes they cause cancer. So that's the electromagnetic spectrum. All of it, though, is light. Okay. I wanted to touch upon a couple of things. First of all, I said that microwaves are used in sending TV signals. That's kind of an important thing to recognize with light waves. How fast do these travel? How fast does all light travel?
3
That's 300 million meters per second. So if you have the Super Bowl, say the Super Bowl is being played in New York, how can we watch it live here?
It's like this, like through the television, the speed of light.
They're sending that signal. Microwaves are traveling at the speed of light. That's really fast. So we're basically watching it alive. And so that's one of the cool things about these waves is we can use them to help us. Your cell phones, a lot of things, GPS navigation, a lot of things use these waves, and it helps us. And technology is built upon waves that travel at the speed of light, and radio waves. Get radio as well. Okay, one more thing I want to touch upon. When you move this way across the electromagnetic spectrum, what's happening to energy as we go to gamma rays? Energy is doing what? Goes up. Okay? What happens if we go this way? What's going up if we move this way? Wavelength is going up. So that symbol for wavelength, lambda goes up if you come to this side. What also increases as you move to the right on this slide? Frequency, good. Frequency is given that Greek letter nu. So frequency goes up. So frequency and energy, what kind of relationship do they have? Is that direct or indirect? Direct. If one goes up, the other one goes up. But what about energy and wavelength? If wavelength goes up, what happens to energy? Goes down. What kind of relationship is that? That's an inverse relationship. Okay. What color has the most energy that we can see? Violet. Which color has the lowest energy that we can see? Red has the lowest energy. Okay. All right, John. Okay, this is just the visible spectrum. Shows the same thing. Again, the visible spectrum, we can see from 400 nanometers to 700 nanometer wavelengths of light. Okay, let's get to what causes light. This is the interesting part. This is where chemistry comes into it. Okay, remember the Bohr model of the atom, Niels Bohr? What did he say the electrons were doing? They were traveling around the nucleus, and what did he call these circular paths?
Energy levels.
Energy levels. So this is energy level 1. There's an energy level just above it that's more energetic, energy level 2. And it goes all the way out. Okay, we just keep going. Remember, energy level 1 is the lowest energy. That's where it's very stable. As you move farther out from the nucleus, like out here, getting more and more energy. They're more and more energetic out there in those further energy levels. Okay, we're going to use this model of the atom to explain how light is emitted from the atom. We're going to actually learn how light comes from the electrons. What causes that? And that's the interesting part in terms of chemistry. Okay, when an atom gains energy, it moves its electrons up to higher energy levels. So instead of being in that first energy level, so this is the nucleus, this would be energy level 1, this would be energy level 2. Energy level 1 and 2. Now, if the electron is normally in energy level number 1, how can we get it to a higher energy level? Well, we've got to have an input of energy. Either you're going to heat it up, you're going to pass electricity through it. Somehow you've got to give it more energy. Okay? And then that electron slides up here into the second energy level. Okay? When an electron is at a higher energy level, it is said to be in an excited state. So if it's normally in energy level 1, you give it energy, say we're heating it up in a flame, it moves that electron to the second energy level. Now it's in an excited state. Okay? That electron is said to be in an excited state. Well, the excited state is unstable. It's very unstable. And the electron wants to return back to its original energy level. It wants to come back down. And this happens quickly. It doesn't like to be unstable. It doesn't like that much energy. It wants to come back down to where it usually is. The original energy level of the electron is called the ground state. So this energy level 1 is called ground state. What did we call it when it went up to energy level 2? That's the excited state. Okay? So it wants to come back to its ground state, because ground state is very stable. This is where it's most comfortable, it's very stable. It wants to be back to where it was. Okay? So here's another diagram that shows ground state and excited state. I want to go through it real fast. It doesn't show the energy level here, but that's its ground state, energy level 1. Okay? Well, energy level 1 is right there. Now where's it at, guys? Energy level number 2. How did it get up there? How can an electron go from energy level 1 up to energy level 2? How do we do that? If energy level 2 has more energy, how did we do it? We had to give it energy, either heat it up or pass electricity through it. You got to have an input of energy to get that electron up to the excited state. Does it like to be in the excited state? No. It wants to come back to ground state, and it will do that almost immediately. Okay. But it's very important. There has to be an input of energy here, and then when it comes back down, can you just destroy energy? Nope. You can't destroy it, so it's given off. Okay, that energy is given back, and that's where light comes from. So let's talk about that. So it is when the electron returns to ground state that the energy is released in the form of light. Okay, so we're talking about it's when the electron returns to its ground state that the energy is released. That energy that it gained before is now given back in the form of light. So, how do we get different colors of light? The color of light that is emitted, that is given off, depends on how many energy levels the electron had to move to get back to its ground state. Let's draw the atom here. This is energy level 1, and this is energy level 2. Now, let's say the electron is at its ground state in energy level 1. You give it some energy, you heat it up, it comes up to energy level 2. It doesn't like to be in that excited state. It falls back down, so it gives that energy off in the form of light. What color do you think it would give off if it's just one energy level difference? Red. How come red? You're right. How come? It's the lowest energetic color that we can see, right? Red. How do you think we would get violet, which is the most energetic color we can see? Yeah, you got to give it a ton of energy. Get it out here into one of these higher energy levels, and then when it comes back down, it's going to give off a violet light.
I can see that. That's cool.
Okay. But these bulbs here are releasing white light, and the sun is white light. How is it giving off white light? Yeah, this is happening all simultaneously. So all the lights, all of ROYGbIr happening at the same time gives off white light. So, okay, for example, if an electron moves from the second energy level to the first, which we just showed there, a red light will be emitted. If the energy difference is larger, a more energetic light wave like violet will be emitted. Okay, so that's where the colors come from that we can see. All right, this is just another diagram that explains kind of the same concept. If we see this electron and it moves back down, how many energy levels? Just one. What color of light was given off?
Red.
Red. It's the lowest energetic color we can see. How did violet form here? Well, it moved down the most energy levels, way more than just one. So 1, 2, 3, 4 energy levels. And then you got green and blue and orange, and all these other colors are somewhere in between. Okay. Here's another slide that shows it in a little bit different format. This is a graph. Whenever you get a graph, it's always useful to, the best thing you should do is read the axes. So this y-axis is the energy of the hydrogen atom. So energy increases as you move up. Okay? And then we've got, let me see if I can move this out of the way. We've got the energy levels plotted here. Okay, all the way up to infinity there. If the electron only falls one energy level, we give off a red light. And then blue would be 2 or 3, and then violet's even more than that. So it's just showing the same thing, just a little bit different format. Okay. Again, just a different way of looking at this. If it only moves one energy level, red. To get violet, you got to move the most. So. Okay, practice problem number 13. We'll end the video on this practice problem. Now, guys, I know I didn't give you enough room here, but if you will draw this, I know you're going to have to draw it really small, but on the bottom of this page, quickly do that. If you're watching the video, please draw that at the bottom of your page, and then we'll talk about it, the question. Okay, so let's answer this practice problem number 13. It says, given the Bohr model of the atom below, identify which color of light would result from each of the following electron transitions. Okay, I want you to write this somewhere by practice problem number 13. ROYGbIr. It's an easy way to remember all the colors that we can see in the rainbow. Okay, now we're gonna use all of these colors in this practice problem. So what color do you think would be given off, guys, if the electron was here in its ground state in energy level 1, you give it a little bit of energy so it moves to energy level 2, and then it doesn't like to be in that excited state. It falls back down to its ground state, but it has to give that energy back. Remember, you had to give it energy. Now it's going to give that energy back in the form of a, what color light?
Red.
Red. Perfect. So that's going to be a red light. So A is red. You guys take a second now. You guys take a second and see if you can get the rest of these. It goes all the way to G. So I'm going to pause the video. If you're watching, pause it, see if you can get the rest of them right, and we'll continue here in a second. Okay, so now let's go to B, the third energy level, and it falls back to the first energy level. So now you're giving this electron a little bit more energy. Get it up here to the third. When it comes back down, what color of light would it give off, guys?
Orange.
Yeah, the next least energetic color is orange. So, and then isn't it going to go just kind of in order, right? So you go to the fourth one, which is a little more energy. Now it's got a little more energy to give back as it comes back down to its ground state. What color?
Yellow.
Yellow. Okay. D. Now you're going up to the fifth energy level. Comes back down. What color of light? This is going to be green. Okay, and that's the next most energetic color. Okay. What about if you go up to the sixth and then it falls back down to ground state? What color? Blue. Okay, and then so forth. You go to the seventh, come back down, a little more energy is given back in the form of light. So now what color? Indigo. Okay, and then finally you go up to the highest energy level, come back down, the ground state. What color? Violet. Okay, perfect. So that's how all the different colors of light is formed from the atom. What particle in the atom is giving off light? The electron. Okay, now a couple of questions I always get. Is light given off when the electron goes up to the excited state, or is it when it comes back down to its ground state? What do you guys think? When it comes back down. Always remember that. You have to give it energy. That's why in these bulbs, you have to turn on the electricity. It's given energy to those atoms. That's not what causes light, though. It's when those electrons come back down to the ground state that light is given off. Okay. Another question I always get. Well, this is all the colors of the rainbow, but how are these light bulbs in the sun giving off white light? How? What is white light? Yeah, this is happening simultaneously. When you do that, when you're having electrons move from all these different energy levels at the same time, then you get white. A mixture of all of these is going to be white light.
And the dark is like black is like none of them.
Good, yeah, black. Every year somebody says, well, how do you get black light? Black light is like an oxymoron, right? Black is actually the absence of light. So there's no such thing as black light. It really isn't. I know they sell those black light bulbs, but it's not really black light, is it?
Violet.
Yeah. Fluorescence is happening there. Anyway, we won't get into that, but black is the absence of light. So if you're wearing a black shirt, what's happening? The white light coming from the sun is doing what? It's absorbing all the colors, isn't it? And that's why it looks black, because there's no light. So if there's nothing being reflected, our eyes don't see anything, and we perceive it as being black. Anyway, so interesting stuff. That is how light is formed from the atom. But before I end the video, let's review. What color has the most energy? Violet. Which color has the least energy?
Red.
Red. So if you just remember ROYGbIr, isn't it already in order of least to most energy?
Yeah.
Sure. What a great way to remember it. But be careful, because they'll sometimes ask you questions like this. Which color has the largest wavelength? Red has the largest wavelength. Which one has the smallest wavelength? Violet. And then they might ask you questions about the frequency. Which color has the highest frequency that we can see? Highest frequency means frequency, how frequent it is. So which one has the highest frequency? Violet. Which one has the lowest frequency? Red. Okay. So as long as we understand energy, wavelength, and frequency of these different colors, how light is emitted from the electron when it comes back down to its ground state, I think we're good. So we're going to do a flame test demonstration, and then you're going to do a flame test lab. So this will help you in understanding the demonstration and also the lab that you're going to do. Hopefully that helped.